With many tools that we have right now when it comes to building AI-based applications or building Gen AI applications, it's actually getting easier in so many ways because we do have all these great tools that are coming up, and as well as techniques that are coming up pretty much every day. So that's the good news. Now, the not so good news, I would say, is the fact that when we want to build Gen AI applications that are secure, that are scalable, and they will perform well, efficient, we need to think differently. We need to understand certain techniques when it comes to architecting or the architecture of scalable, secure, and efficient Gen AI applications. So in this video, I'm going to show you, at least as an overview, on how you would go about architecting Gen AI applications. And I think this is very important because now we're beyond just putting together Gen AI applications, but we're now thinking on how the architecture of a Gen AI application and why is it important, and all of the things that you need to understand in order to build secure, scalable, and efficient Gen AI applications. So that's what we're going to be doing in this video, and I hope you enjoy this. Let's go ahead and get started. So now let's do a Gen AI deep dive. So what we're going to do is we're going to learn what is Gen AI. So we'll understand the motivation behind it. Also look at advantages, disadvantages, and key concepts of Gen AI. We're also going to look about traditional machine learning versus Gen AI. So what is this thing called Gen AI? Gen AI is generative artificial intelligence. So what it does is it uses these algorithms, machine learning algorithms that are very powerful, that allows us to create or generate, hence the name generative, content that is actually original, but from a knowledge base. So the idea is that this original content that is generated can be in different forms. It can be images, text, videos, and audio. So essentially you have input prompts that you say X, Y, and Z, and goes through this AI, artificial intelligence, this black box, and then spits out the actual content. So this is what Gen AI essentially is. Now let's look at some examples of Gen AI technologies. So the first one you have seen and used, I'm sure, is ChatGPT. This is what we call the text generation AI. So the idea is simple. We have input as prompts that would say, for instance, write a poem about self-regenerating robots. And that will be sent into this machine, this AI, right, neural network, and then it will spit out the actual text, right? It will generate the textual content. Here are some real-life applications for these cases. We have communications, journalism, publishing, right? Publishing papers or publishing textual or blogs and so forth, creative writing, and as writing assistant. So we can use this text generation AI technology to generate content, textual content in this case. But we also have other ways of generating content or different types of content that can be generated. One example is Midjourney. So this is what we call image generation AI. So the idea is still the same. You have the input. You can say a dog running while eating ice cream, and that is sent out into the AI, and then it spits out an actual image of a dog running while eating ice cream. Okay? So some real life applicabilities or applications for this case, you can see we can use that for advertisements in the advertising industry to create images for advertising. We can create those images for publishing as illustrations. Also for corporate visuals, let's say you're creating, in this case, some sort of slide deck for a presentation, and you can include those visuals to enhance your presentation. Also, novel image generation for people who are creating novels, writing novels, they can also create those images for that. And then we have computer coding generation, AI. So in this case here, we have the same concept where we have input, such as write a tic-tac-toe console program in Python, as an example. And of course, the generation AI will go ahead and create the code that we can then run and see if it works. Okay, so some real life applications here would be in web design, software development, of course, coding or scripting technologies, and so forth. And you can also use for debugging or pair coding. Okay, so a lot of real life applications for GenAI. Let's look at an overview of some of other practical applications of GenAI. So as we looked before, we talked about content creation. This is a huge one. So writers can use these tools to write or help write whatever they're writing, artists and so forth. So this is a growing industry at this point because a lot of people are starting to use these powerful GenAI applications to aid them in their process of writing, and artists also use that for creating all sorts of things. And also natural language processing, NLP. So you've seen chatbots, language translation, content summarization, also in medical imaging and diagnosis. So we have GenAI systems that are able to interpret, in this case, medical images to create a diagnosis, and also be able to generate detailed images of certain conditions, medical conditions, and so forth. So a lot of amazing things are happening there. But also we have video game development, so the creation of very realistic environments, characters, storylines, images, and worlds, and so forth. And financial forecasting, so being able to use these tools, these GenAI applications, to analyze data that pertain to finances, economy, and so forth. But also we have the drug discovery. So here we're able to use these tools, GenAI tools, to, for instance, predict a certain molecular structure that can potentially solve a problem or create a drug that can help people get better. So these are some of the practical applications of GenAI. Obviously, there are many, many others, but I just want to give you some overview. So we're going to look at traditional machine learning to what we have now, generative AI. In traditional machine learning, the process typically involves a few steps. So the first step that happens is that we have this process or this step where there is the data pre-processing. This is where the cleaning and the preparation of data for analysis, for instance, removing duplicates, handling missing values, and so forth. This is where everything happens. So this pre-processing ensures that the data is in a usable format for training. And so then we go to the next step, which is the future engineering. So here, all that's happening, or part of things that is happening, is there is this extraction of the meaningful features from the raw data. Feature engineering helps highlight important aspects of the data that eventually a model should focus on for predictions. And the next step is what we call training and tuning. So here's where the training of the models using the prepared data previously, and there is also the adjustment process of the parameters so that everything is optimized for good performance. This includes, for instance, selecting the hyperparameters, experimenting with model architectures, and validating results to make sure everything is trained well and everything is tuned. And then we have the deployment and the monitoring. This is also a very important step because this is where we are implementing what we have trained, right? The things that happened before, in this case, the trained models, now in the real world applications. So the ongoing monitoring has to happen because it's important to know how the trained model is behaving, if there are issues that need to be addressed, and so forth. So the idea is to make sure that the model continues to perform well, especially when new data comes in. So usually the tech stack that would involve such structure here would be the machine learning frameworks such as Keras or Theano, and also machine learning APIs and SDKs. There are many out there, but one of which would be, for instance, IBM Watson, and database, SQL Server, Oracle, many others, and of course machine learning ops, in this case all the tools that allow for the entire workflow to work. In this case, Docker, Jenkins could be one of part of this tech stack. Now, next we have the generative AI, which is what we are interested in looking into. The process is still the same in many ways, but with some differences. So we still have, of course, the data preprocessing side of things. So this is similar to traditional machine learning. And then the next step here is prompt engineering and fine tuning. Instead of what we had before, which was feature engineering, GenAI in this case focuses on prompt engineering. Okay, so the goal here is to design effective prompts that guide language models, LLMs, to generate desired outputs. So there's also fine-tuning that's happening. Now, fine-tuning foundational models on specific tasks can also play a role in adapting these models to a particular domain. And the next step, of course, is what we call foundational, also fine-tuning large language models. It's important to know that generative AI uses large pre-trained models such as GPT, which is generative pre-trained transformers, to, in this case, generate content. Now, these models can be fine-tuned on specific data sets to, of course, improve performance for a given task. Now, the key difference from traditional machine learning is that the model comes already pre-trained on a massive data set and only needs minor fine-tuning, or in this case, prompt adjustment. So those are the differences between traditional machine learning in this case and generative AI. And the next step here, which is deployment and monitoring, similar to traditional machine learning, GenAI models are also deployed in production environments and need to be monitored, you know why, to ensure that they also perform well over time. Generally speaking, generative AI would have a tech stack that would include a GenAI orchestration. In this case, would use Llama Index, or LangChain, or many others out there. And of course, at the center of everything would have to have a large language model. Okay, would we use OpenAI models, or Anthropic, or many others models out there? And because the idea is to save information into the vector space, we would also need a vector database. So we could use Pinecone, Weaviate, or Chroma, and many others out there. So we'll have some ops that will be included in the large language model for prompt layer, or in this case, Helicone, and many others out there. So this is just a general tech stack that you would see in generative AI. Okay, so here are some popular GenAI models. We have ChatGPT. We've seen this before. This is the chatbot by OpenAI. So the simplistic form of, I would say, of a model, because it allows users to refine and help steer the information they want to get back. So it's more of a conversational, where the user can pass in a prompt and refine the prompt to get the result that they want, the outcome that they want. We've seen DALL-E, also by OpenAI. So this allows users to create realistic images themselves. These are original images, of course, by passing in short text description as prompts. There is also Stable Diffusion. This is what we call text-to-image model by Stability AI. And of course, OpenAI Codex by OpenAI, of course, that allows, again, users to pass in prompt in the natural language format, which then is parsed to generate code as response. And of course, there are many, many others out there, but these are some of the most popular GenAI models out there. So it's important to know that generative models are the algorithms or models that make GenAI applications work. Now, these models are, of course, trained on large sets of data, such as text, images, or sounds, to understand, in this case, the patterns. After learning, they can create new data similar to the training data, but unique. So that is the base of GenAI, is that the model itself was pre-trained on these huge amounts of data sets, but now we're able to inject or to ask to pass our own short messages, and it's able to take the message, and with this data set that it was trained on, this knowledge base, it's able to generate something unique, something new for us. So when it comes to generative models, we have different types. We have variational, autoencoders, so VAEs, and we also have generative adversarial networks, GANs. Let's take a look at each one of those so we hopefully have some understanding on how they work. The way I like to think of VAEs, I like to think them as a kind of generative model that learns a hidden talent, in this case, structure of data. This hidden structure lets the model create new data that shares characteristics with the original data. So a simple example would be, for instance, imagine we have a VAE as a machine that learns to compress and then creates images of cats. So after training, it can also generate new pictures that look like real cats but have never been seen before. So the idea is that the model learns a hidden talent. In this case, we say, well, here is images of cats. And then this hidden structure lets the model then create a new data that shares characteristics with the original data. So in this case, new cats will be generated because these have same characteristics, similar characteristics with same data that this model was trained on. On the other hand, when it comes to generative adversarial networks, these involve two models working against each other. So on one hand, we have what we call the generator, and then we have the discriminator. So you can imagine that the generator is the one that tries to create new data, like in this case, fake images, and the discriminator tries to figure out if the data is real or fake. So these two models compete to improve each other. So the generator keeps trying to fool the discriminator, and the discriminator keeps getting better at spotting the fake data. So think of it like a student, in this case could be considered a generator, trying to fake a signature, while a teacher, the discriminator, tries to tell if it's real or not. So the more they practice, the better they both get. Okay, so let's look at a diagram so you can see how it all works. So at the top of everything, we have this noise input C. So essentially, it's a random input that is fed into the generator. It's an input to create fake data that is passed down to the generator G. So this one is one that actually generates the fake data, for instance, images, as we have been talking about, which then creates the fake data. So, and alongside, we will have real data. But the fake data goes through both of them, in this case, fake data generated and the real data. They go through the classification, right? So in this case, the discriminator gets this information and tries to differentiate between real and fake data. And of course, there is an output. So the output could be real or fake. So this is the discriminator's decision to decide whether it's real or fake. The beauty here is that there is a process that goes in as a loop. So there's the feedback to the generator. Again, the same information that we receive, the output, is fed back to the generator and create fake data, and the real data is still there and goes through the process. So essentially, we're training the whole workflow, this whole system, so that they get good at what they do, at detecting something that is false and also at generating what is fake, so that both of them can continue to compete with each other, which essentially will make the whole system even better. So this process will continue until the generator becomes good enough that the discriminator can't easily distinguish between real and fake data. Now let's bring it all together in the context of large language models with an example. So we saw that we have these generative models, right, which we have two variational autoencoders, VAEs, and the generative adversarial networks, GANs, right? And so all of that put in together, we will also have what we call the adversarial learning. So the idea here is that the two models are trained together. So one, we have the generator, and then we have the discriminator. This is the training technique used in models like GANs, right? These generative adversarial networks, because there's always this clashing or this competitiveness happening between these two models. So essentially, two models are trained together. So one tries to create fake data, that is the generator, and the other tries to detect the fake data, which in this case is the discriminator. So over time, again, the generator gets better at making data that looks real, and the discriminator gets better at spotting fake data. So you can see that this back and forth competition helps both models improve. And it's the whole point of having a model that works really well. So think of it as a constant game of cat and mouse, where both the cat and the mouse get smarter as they play. So in summary, generative models, they create new data based on existing data. That's the beauty of these generative AI models. So we have looked into VAEs, so variational autoencoders. So these learn hidden features, right, in data to create similar but new data. Very important distinction. Okay. And then we have GANs, so generative adversarial networks. Now, these are the models that have the system where they compete against each other to improve detection. And so adversarial learning is this battle or a training technique where two models, in this case the generator and the discriminator, help each other improve by competing. That is the basis of these two kinds of generative models. Gen AI applications have many benefits. One of which is that they increase efficiency because now we can use them to automate our work and save time. And also enhanced creativity because it allows for the generation of new ideas, new content from these systems, from these models that have been trained on large data sets. So essentially they have the brain of the world essentially that we can tap into, but yet we generate something completely different from the data or from data sets or from the knowledge base from those large language models. And also allows this personalized experience because we're able to customize the content and recommendation based on user. You've seen many applications where it recommends or it customizes information depending on the user. So for instance, recommendation systems for e-commerce or recommendation systems for learning. Let's say you start learning X, Y, and Z, and then a system that is model-based or GenAI based is able to know, quote unquote, your patterns so that next time it will recommend you something that is customized to you. The other one is drug discovery and material science. Now, it's amazing how actually GenAI applications are able to accelerate innovation and scientific research because of this pool of data that it has, but we also can include our own data so that it can leverage this knowledge base that is there. But it's not all just this river of roses and flowers. Everything is wonderful. There are also challenges of building GenAI applications, one of which is bias and fairness. So there is a risk of perpetuating biases depending on what the model was trained on. And this has been a problem, and that is being mitigated. And a lot of papers, a lot of innovations on that area are being built right now to make sure that indeed these GenAI applications that are being fed or being held together by models, they need to be fair in every sense of the way. Also, security concerns, because it is possible that these are generating harmful content and are being misused by bad actors who want to take advantage of people or exploit systems. So as you know, models have a lot of data, right, or are trained on a lot of data, and they can be hard to interpret. So when something is hard to interpret, when a user cannot understand how, for instance, a model got to a certain answer or to a certain response, it is very difficult for a user to be able to trust that model or that information. And so that is one of the challenges of building GenAI application, is that it's very complicated to have people trusting, especially when they can't explain or the models are not able to show the explanation or are able to explain how they got to a certain answer or response. And also we have computational costs. As you know, these infrastructures are resource hungry, so they demand a lot of resources, and that can get very expensive. but also not just expensive monetarily or financially, but also in terms of resources, general resources of electricity and power and many, many others. So these are some of the challenges of building GenAI applications. It is now time to look into the LGPL architecture. So the idea here is that we're going to look into the core principles of LGPL, so we're going to understand what that is. It's essentially going through the architecture, understanding why architecture is needed for GenAI applications, and what is this LGPL acronym thing. And then we're going to do a deep dive into each LGPL component. So first, maybe we need to ask the question, why do we need a proven architecture for GenAI applications? Now, it's a very obvious question, of course, and you may know the answer, but there are some nuances that we are going to demystify as we go through. GenAI applications, as we know, are very complex because they involve a lot of things, a lot of data, training large models, and also making sure that sometimes you need to deliver real-time responses. With all of that, that means that having a proven architecture is obviously crucial for the following reasons. One, complexity, as we talked about, the complexity in management. As we know, GenAI applications have lots of moving parts because they involve handling data, vast data, I should say, training large models, and also, in some cases, delivering real-time responses. So an architecture helps organize this complexity into manageable pieces or components. And the other one is scalability. Generative models like GPT require significant computational resources because they're large, they require a lot, they are resources hungry. So an architecture ensures the system itself can scale efficiently as demand grows and scale down as demand diminishes. The other one is modularity. So breaking the system into layers, so for instance, data layer, model layer, application layer, and so forth. This allows independent optimization, updates, and maintenance. So if you have these small pieces, it's easy to, for instance, if you want to scale the layer, the data side of things, or change the data side of things, it's easier, and then scale or change something in the model layer side of things or in the application. So it's nice to have this modularity. So we break down the system into layers. Okay, easier for maintenance, updates, and optimization. And we have security and compliance. Now, this is very important because having an architecture, then we would know that it will provide gates for data validation, security, and compliance checks. So essentially, making sure that we have everything that we need to protect sensitive information and ensuring the adherence to regulations, which is a huge part of building GenAI applications. So having architecture allows us to at some point have what we call pipelines. So these streamline the flow of data and the tasks between each layer, which obviously improve the overall performance and also minimizing latency. So how fast things are going, how long it takes for things to happen. Now, all of this is very critical, especially for real-time applications. So in summary, a well-designed architecture is extremely important. It's vital even for building scalable, secure, and efficient GenAI applications that are able or capable of continuously improvement and performance optimization. To truly understand the LGPL architecture in the context of generative AI application development, we need to break down each component, in this case layers, gates, pipes, and loops, into their distinct roles and how they kind of fit together to form this functional, scalable, and of course, secure architecture. So essentially what we have is layers, gates, pipes, and loops. Now, if you look at an analogy of a building as a house or a building in general, okay, layers are like different floors, and each floor performs a specific function. So essentially, we would have this structure here. So we have the application layer at the top, we have the model layer, data layer, and the infrastructure layer. So each one of these has a specific function. So the application layer would, of course, deal with the user interaction, the user interface essentially. The model layer will deal with AI models. In this case, it would be GPT or any other model that's been used. And the data layer, as the name implies, this is where we are storing data pertaining to our application. Okay, and then we have the infrastructure layer. This is where we have the cloud platform, servers, monitoring and logging and all of that. Okay, so it's important to have these layers because this is part of structuring, of architecting our Gen application. So important to know that the data layer is the foundation. So it stores the input data, in this case could be text, images, and so many other things, and makes it accessible to the next layers. The model layer, it's also important, of course, all of them are. So this is what we call, I guess, the processing floor. So where the AI models like GPT, DALL-E, and so forth, this is where they're trained or used for inference. And then, of course, we have the application layer. As we said, this is the interaction floor, if you go back to the building analogy, because this is where it handles the user interfaces. So this is part of the APIs and client interactions. The infrastructure layer is the structural support. It's almost like the foundation because this is what includes cloud services, AWS, for instance, or GCP or Azure, okay, which includes servers and computational resources. So this is what layers is all about. So we've talked about layers previously, and now we're going to talk about the next step or the next letter in the LGPL acronym here, which is going to be gates. So gates are essentially these control points between layers. So imagine that we have a layer at the top, for instance, could be an application layer, and at the bottom we'll have this model layer. So the gate is what is inside or between these two layers, right? Because this serves as the validation between these two layers. So when the data is pushed through from, for instance, application layer, it goes through the validation, which is in this case the gate. This is the validation gate. So think of gates as the security checkpoints in a building. So you have a building, you have security checkpoints, everybody has to go through. Okay, that's why it's validation. So you can't go from one floor to another without passing through a gate. Why is this important? Well, this is important because gates ensure the correct flow of information and make sure that everything is protected, or the system as a whole is protected against errors. So that is the flow that we have between data that goes through one layer to the next. It has to go through this validation, this gate, this security checkpoint, if you will. Now, there are different kinds of gates. So we have what we call the security gate. So this is the one that ensures that only authorized users or data can access certain layers. Okay. For example, we could say only clean validated data can go from data layer to the model layer. That will be the job of security gate. We also have what we call the compliance gate. Now, the compliance gate is important as well because before storing user data, it is responsible to check if it meets regulatory requirements for such as GDPR and other requirements are needed. And of course, we saw the validation gate, which, as you know, before sending data for inference, a gate checks if the format is correct and ensures quality. So that is the importance of gates, and that's what gates do. So next, we're going to talk about pipes or pipelines. Either one of those that works. Pipelines or pipes, same thing. So what are these? So pipelines are just like conveyor belts. So they move data between different layers. They ensure that there's this movement of data, which is very crucial, but not just a random movement. The movement has to be smooth and efficient because that is important for the health of the entire system. Okay, so this movement has to go from one part of the system to another. So think of pipelines or pipes as the elevators in a building that transport people, data in this case, between floors. So here's a simple diagram. So we have data that needs to move through a data pipeline or data pipe. So the data pipeline or data pipe moves that data to the model layer. So the whole responsibility really is to move raw data from the data layer to the model layer for pre-processing and training. Now we also have another kind of pipeline or another kind of pipe. This is called the inference pipeline. So the inference pipeline, as you can see here, has as input data a prompt, which is just a description that we can type, or a textual description of what needs to happen or what we need to get results from our large language model or the model itself. Here it's a little bit different because now it moves input data. It's important distinction here for data pipeline moves raw data from the data layer to the model layer. Whereas when we talk about the inference pipeline, this is responsible for moving input data from users, again, prompt for text generation, to, in this case, the model layer for real-time inference, and then returns the result back to the user. So that is the difference. One is raw data, the data pipeline, and inference pipeline feeds or pull in the data from users, example, prompt for text generation, to the model layer. In any architecture, having a feedback mechanism is very important because that is what feeds the whole system so that it continues to grow and continues to relearning and function as a whole. So that's when loops, as part of the LGPL architecture, comes in. So loops is essentially a feedback mechanism. So loops are a feedback mechanism that allows for the refinement and or improvement of the system, as I've mentioned. This has to be this constant refinement and improvement of the system so that the system continues to grow, learning, and do what it's supposed to do. Think of them, in this case, these loops as feedback mechanisms. Think of them as a communication lines between different floors of the building. In this case, we have user feedback, and this is fed into the model training, and the model training will retrain itself based on that feedback loop. So you can see that we have that feedback that continues going as such. So the feedback mechanism is divided into different parts. So we have the training loop, which continuously feeds new data back into the model to improve its accuracy over time. For example, retraining the generative AI model with updated data sets. And then we have the user feedback loop. As the name implies, this is the data or information that comes from users that users provide as feedback on the model's output. For instance, when somebody flags incorrect responses. So that would be a user output or input, I should say, or feedback loop, I should say. Okay, so what does it do? Well, this helps improve future outputs. And we have the monitoring loop. So the monitoring loop, this constantly checks the system's performance. So make sure that things are going well by looking at, for instance, the response time, the accuracy, and so forth. So it provides, again, feedback to optimize the infrastructure. Okay, so now bring it all together. We know that we learned about layers. So these are the different components of the architecture, the GenAI architecture, which in this case has data, model, application, and the infrastructure. And then we looked at the gates. So these are the checkpoints that make sure that everything is secure, compliant, and there's this data validation before moving between those layers. And then we have pipelines or pipes. These are just like conveyor belts or elevators that move data between layers. And then we look at loops. So it's just a feedback mechanism for system refinement, system improvement over time. Now, looking at the diagram here, this is just a summary of what we have just looked at. So we have the application layer at the top. So this is the user interaction, the APIs, and so forth. We have the inference pipeline. So this is real-time data flow. We have model layer. So this is where we have the AI models, GPT or Llama or any other model you may have. Data pipeline. This is where the data is moving. So this allows the moving of raw data for training. Data layer, this is where the data is stored, or at least has the way of pre-processing and storage of data. And then we have the infrastructure layer. This is where we connect to cloud, platform, servers, monitoring and logging and all of that. If we look at all of this as a summary, or if we want to use an analogy, we can say that layers are like the floors of a building. So each floor having, in this case, a specific function, okay, as we saw. And gates are the security checkpoints ensuring only valid and authorized movement between floors. Pipelines or pipes, in this case, these are just the elevators, right? These are the conveyor belts. These are moving data smoothly between the layers. And loops, very important, is a system of feedback. Okay, so feedback system constantly refining and improving the building's operations, like regular checks and making sure everything is working smoothly. This is the whole structure, the whole architecture we've talked about. In this case, the LGPL architecture. So now I'm going to show you a very simplistic scenario here where we're going to do a hands-on for doing a gate simulation. This is extremely simplistic, of course, but it's hopefully going to help you understand exactly how this in real world could be implemented. Again, very simplistic, but we're going to do it. So essentially imagine that you're creating a GenAI application that summarizes text, okay? And so the idea is that users are able to upload a certain document for summarization. So we are going to make it so that we have a premium and the free user side of things. So the free user can upload up to 10 kilobytes limit of the document limit size. Whereas for the premium user, there's no document size limit. The steps would be: one, we would define user roles. In this case, we said free user, up to 10 kilobytes limit. And for premium user, no document size limit. And so the second part would be to simulate, in this case, the first part, which is the user login. And then third part, access control gate. And then simulate document processing. All right, let's go ahead. I'm going to show you how all of this works in code. Again, very simplistic. The idea here is not the code, but it's just the concept. All right, so I have the code here. So simulated user data. So I have this user data here. We have user 1 and user 2, a dictionary with password and role free, and role is premium for the second user, and password is password 2. All right. So there we go. And then we have the user login simulation. So we are going to expect input for username and the password, and we get that information and we check to make sure whether the password is correct. The credentials are invalid, we just say credentials are invalid. And then we have the document upload gate. So this is where we are using the concept of the gate, right, to make sure that we have this security system here before anything happens. Okay, so in this case, it's going to be based on user input document size. We can ask them to enter the document input size. Of course, in a real world application, you would calculate that, which we'll see in a little more advanced version of this simple code here. And so once they input that, we're going to check to make sure that everything is great. We're going to make sure that we have the size limit here that we specify. So if role is free and document size is greater than the limit, then we're going to not allow users to do anything. In any case, we're going to go ahead and summarize the document. So the summarization of the document here is very simple. Of course, we're just simulating. So this is where you would use the large language model to do the whole processing. So as you can see here, the login function returns the user role. So we're going to use that to check, and depending on the situation, we're going to allow them to upload or not. Okay, let's go ahead and run this real quick. So I'm going to say user 1, for instance. I'm going to say password 1. So all of that is pre-written, as you saw in the user data. Okay, enter the size of the document. I'm going to enter a very large size. You can see this is not going to work. So, okay. You can see document size is that. Document size exceeds limit for free users. Very good, so that works. Let me go ahead and run again. In this case, I'm going to use user 2 because I know this is going to be the pro user. Password 2. So it doesn't matter what size I add, I'm going to be able to get in through the gates, and then I'm going to be able to have the document processed. Okay, very, very simplistic. Obviously, you're not going to take this and put into production, but at least, if anything, it works as a little relief from learning all these concepts we've learned. But at least you can see the basics when we talk about gates, different, to make sure that we have these checkpoints in place between all those layers. All right, so in this next example here, I'm going to simulate the user feedback loop. So that way we can improve potentially the model. Again, extremely simplified here, just for fun, but at least it's going to hopefully show you a little bit of the mechanics as you would implement this in your systems. All right, so same thing, we have the user data as we saw before. We have this dictionary, empty dictionary, where we're gonna add as we go all the feedback loop as things happen internally. And then we have this adjust model based on feedback. So it's very really simple. What we're doing here is that we are adjusting the model, which we don't have the model here, but we're just simulating based on the feedback. So here we're just simulating a simple AI model, which is going to adjust its quote-unquote quality, as I put here, based on feedback. So nothing really out of this world here. Okay, so we still have the user login to make sure that the credentials and the limits for the document size are there, but this one specifically for the credentials. And then the upload, everything that we've seen before. And then the summarization as well that's happening here. So in the summarize document, we're passing the document. So the document summarization, in this case, this would be the model layer. This is important. And I've added all of this so you can see the differences. So data validation gate and access control. This is the gate. Okay. And so we have the document summarization model layer, as you saw. So here we're adjusting again, summary based on feedback, the model layer. And then we do all this stuff and we simulate the feedback loop. This is what's happening here. So we're calling the gather feedback and pass the summary as we go. Okay. And the simulate feedback or gather feedback here, this is where everything is happening. As I said here, we're simulating the feedback loop. And so the idea, as you will see, it's going to ask how was the summary, and we're going to give the users the chance to say good or bad. And we add to our as a feedback loop into the dictionary. And the whole simulation starts here and all is good. So let's go ahead and run this real quick so you can see. So username, I'm going to just use user2, password 2. So very good. So enter the size, doesn't matter. I'm going to enter just a number, and you can see it says document size is that, but most importantly, summary. This is a sample document for GenAI summarization. This is a sample document for GenAI summarization, ... Okay, so this is just again, a simple simulation. So the feedback starts here. How was the summary? Now I'm going to say good. And then it asks me, do you want to continue? I'm going to say yes. So it's going to go ahead and ask the same question again. And then it gives me the summary. Potentially would give a different summary because I've potentially added a new document, right? But we're just passing the same thing anyway. And then enter your feedback again. How was the summary? I'm going to say good again. Do you want to continue? I'm going to say no. So the moment I say no, I should have the feedback received so far, and then it spits out this information here. Okay. So the first one, we attach the feedback for the summarization, and the second one, we also attach another feedback. So very simple. So as I go and adding in feedback, it's going to be feeding back to the system to simulate that feedback loop. Again, overly simplified, but I hope you get the idea with this one. All right. So in the next simulation here, we're going to extend what we've done with the previous simulation. So the same premise still. We have the free user and the premium user, and simulate the user login, access control, simulate document pre-processing, processing, and all that. But now we're going to actually do everything, meaning we're going to include all of the layers. Okay, as much as we can, of course, all of the layers we talked about. So this is the code here. Again, don't worry about it. This is just simulation, so you can hopefully understand what's going on. So I'm importing a few things, logging, async CIO. This is to allow us to have this asynchronous data moving around so we can see, kind of simulate a real world application, of course. We have secret, we have SQLite 3 to save in memory as you will see, some of the data for our feedback loop and so forth. Okay. And I'm also passing in or importing here, or install this case, cryptography for encrypting information. This is another added layer for data protection and everything and all that. So also I have to say that I'm actually using OpenAI API to do the actual summarization. So this is something you can do. You have to have, if you want to run this, you have to have OpenAI API key for this to work. And I'm not going to go into these details because that's not the point here. Okay, so I'm loading all the environment variables and make sure that I've also added here must do pip install python.env, OpenAI, and SQLite 3. All right, some configurations are happening there. I'm configuring the SQLite database. So this is the simulation, right? This is the application layer, I should say. So this is for us to be able to store users and feedback. And here is the infrastructure layer. So I'm simulating the infrastructure layer. In this case, I'm going to use the cloud storage for documents. So in real world application, obviously you would have an actual cloud storage. Okay. And here I'm generating and storing the encryption key. Okay. This obviously would be ideally will be saved somewhere very secure. And then we are encrypting a document. So this is the infrastructure layer. I have a function here, just encrypts that document that we pass along. And we also have this decryption that it needs to happen of that document, still part of the infrastructure layer, that function. And then we have the summarization function. This is the model layer. So we're going to actually use DPT3 summarization function with OpenAI API. So that's what I'm doing here. Remember again, in order for this to work on your end, you will have to have the OpenAI key, OpenAI API key, and all of that. But also you can use any other model, find Anthropic and whatever you need. All right, so what I'm doing here is I'm creating a response. So I'm getting that document in text as text, and I'm passing it through the client, the chat completion API to summarize that text, and passing the actual text, which is the content, to go ahead and summarize. Actually, this should be, please summarize the following text. Okay, like that. And of course, I'm getting that summary and I'm returning that information. Okay, so now let's go ahead in the application layer. So we have to use a login with token-based authentication. Of course, that's what you would have. And that's what I've tried to simulate here by using the hashlib hash SHA-256 and all that. Okay, and I'm executing the SQLite table to create the user and everything. Okay, and I'm getting all that information that I need. And then I have the gate. This is the document upload with file size validation and encryption. So this is exactly what we've seen before. So I'm trying to hit all of the layers we've talked about. And we go through the summarization and everything, and all of that is happening inside here. We're using other parts of the infrastructure layer, right? So to read and encrypt the content, for instance, we have the pipeline here. So we are simulating the real-time processing for users, as you see here. Okay, so you can see we say await to simulate that process, the real-time processing. So we're batching processing for premium users by passing the encrypted documents, and append that to our cloud storage, which at this point is just a dictionary we created earlier, or a list. I think it was a dictionary. Okay, so and then we have the model layer here and everything. So this is where we are summarizing the document and do all the things that we need. And then we enter the feedback loop. Okay, so we gather feedback as we saw before. We start inserting things into the database, because this is what you would do in a real world GenAI application. You would save that input so that then you can feed back to the system, to the whole model. All right, so then we start a simulation. Nothing really to write about here. We have the batch processing and we get started. So then we just log information coming in to fetch everything from our database. Okay, this is a simulation again. It's not production, but at least I'm putting everything together so we can see everything working. The first thing is, what's my username? So I'd say user2, give it a password 2. Okay, very good. So you can see it knows that password I'm authenticated. So user authenticated successfully, and even gives me this token that we made up, okay, internally. And then upload a document. So I uploaded the document. And the thing is, actually, this code uploads the document that we have here. I have few documents in the data folder here. So I have Shakespeare, which we don't use. I have a Dream, and the Gettysburg. Okay, so let's continue here. So document upload for batching. Do you want to continue? I'm going to say yes. Okay, very good. And document upload for batching again. Let's just say no in this case because it's repetition. So, right, it's going to go through the process and look at this. So the process is that, again, it got document, exiting simulation, thanks for feedback, batch processing the following documents for premium users, decrypting document, and do all the things, okay, and hit the chat completion API, the real one, by the way. And then it took the document and says here the summary to summarize. So the text is a speech by Martin Luther King, where he expresses a dream, blah, 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 and all these amazing things. So it's really good because it's actually doing the work. It's actually pulling in this I have a dream TXT that I have added there to do the work. Okay. Very good. Now, the beauty here is that how was the summary? So I can say good or bad. I'm going to say good. Was pretty good. And you enter, and it's going to go through the process to adding that information again. So I'm going to go ahead and say good, because it's just on repeat. And then once all is good, it ran a couple times. Feedback received so far, and it gives me this list that contains the summary and the attached feedback that we have added to that response, okay, for each one of these, as you can see here. All right, so this kind of puts together into perspective what we've been talking about with the architecture, right? All of the layers. Okay, so I hope this was helpful. You'll have this code. I would like you to take this code and make it even better for simulation purposes. But the idea is that you see this and you can see how you can use it when you're actually building or architecting your GenAI applications. I hope you enjoyed this mini course, and hopefully this made sense and you're starting to think about going or how to go about building or architecting your GenAI application. Now, this was mini course. If you are interested in learning more or interested in the full course, check out the link in the description where you'll be able to go and enroll in the full course. Thank you so much for your time. If this was of any value to you, I would appreciate if you left a comment. Also, subscribe to this channel and share with other people that you think might find this content useful. I would definitely appreciate that. Thank you so much for your time, and till next time, be well.